So I let a few seconds for people to connect before we start. Donc, attendons quelques secondes le temps que les gens se connectent sur YouTube.
Okay. It's on the.
So I let a few minutes.
Yeah.
Très bien. Nous allons commencer. Donc, je vais passer en anglais aujourd'hui pour cette soutenance. So I'm switching to English. Today we have this PhD defense by Joana, Marques, Oliveira. So Joana, you are presenting today a PhD thesis entitled in French, Explorer le système solaire extérieur au-delà de Neptune en utilisant des occultations stellaires, application à Triton. So in English, that will be exploring the external solar system beyond Neptune using stellar occultations, application to Triton. So it is to obtain the degree of doctor of the Sorbonne Université. So before you go, I will introduce the committee. So I start with Dr. Candice Hansen, who was a rapporteur of the thesis. She is a senior scientist at the Planetary Science Institute in the USA. She's based in Utah. Pascal Rano was the other reporter of the thesis. He's a professor at the University of Reims in France and a researcher at the GSMA lab in Reims. Kathy Olkin she's a thesis examiner. She's a senior scientist at the Southwest Research Institute in Boulder, Colorado, USA. We have Darrell Strobel, thesis examiner, senior scientist at the Johns Hopkins University in Baltimore, USA. Thierry Fouché, examiner, professor at Sorbonne Université and researcher at the LESIA laboratory at Paris Observatory. Bruno Sicardi is the thesis advisor, professor at Sorbonne Université and also a researcher at LESIA, Paris Observatory. And myself, François Forget, I'm a senior scientist at the laboratory LMD in Paris, and I will chair this committee. So now, Joana, we are listening and watching your presentation. I encourage the committee to mute their phone, but maybe to keep their camera if it's possible. So that we can, Joana can see us. So Joana, you can start. You have about 45-50 minutes for your presentation, and then we will exchange questions.
Thank you. So I'll talk about the application of stellar occultations to the case of Triton, with an emphasis of the Triton occultation event of October 5th, 2017. So I will begin with an overview of the stellar occultation technique and then talk a bit about Triton before getting into the results. So stellar occultation event happens when an object, usually from the solar system, passes in front of a star, blocking its light to an observer on Earth. The shadow projected by the object, which is also called the occultation path, can be observed by several locations that we call stations, and the dimming of the star's flux is recorded on each. That then produces an occultation chord, and that depends on the duration of the event and the position of the station. So each station's recording leads to a light curve, shown here. This allows us to study the occulting object. Stellar occultations allowed for the detection of an atmosphere. So it's characterized by the gradual increase and decrease of flux at the beginning and ending of the event, down to an atmospheric level of about 10 nanobars in the best conditions. This technique can probe planetary atmospheres to retrieve the temperature, the pressure, and the number density profiles using the inversion method, under the assumption that the structure of the atmosphere is in hydrostatic equilibrium and that it's composed of an ideal gas. Information can also be obtained using models that are fit to the data, and I'll talk about these two methods later. If the atmosphere is dense enough, the light rays can probe the deepest parts of the atmosphere, and when it passes close or at centrality, and it can cross the central line that connects the star, the object, and the observer. And that causes the detection of a central flash around the mid-event. So in other words, the atmosphere acts like a lens. Central flash allows for a possible detection of hazes, but if absorbing material isn't detected, then we are dealing with refractive occultations, and that's what I'll focus on in this presentation, and then I'll have a discussion about absorbing material later. So I have here another visual for the effects showing the refraction that occurs with the primary image and the secondary images happening. We can see around the middle of the event, the flux of both images is comparable. Their intensity is comparable. And here the red circle is a very exaggerated view of a star. If the atmosphere is transparent, the flux increases as the event approaches the center of the shadow. So when the observer, the object, and the star are perfectly aligned, we reach the maximum value of the observed flux. So here I show a real life example of the primary and secondary images. So this is from a Triton occultation in 2001. This is a occultation of a double star system. This first star is further from centrality, so the secondary image isn't as noticeable. So I'll stop it here. So the flux of this first star goes from the top, and it follows the direction of motion, and we can't see the secondary image. And then for this star, we see, so I'll stop again. So the primary image goes at the bottom of Triton, and the secondary image goes the opposite direction at the top of Triton, and it's very quick. So, and here, because of Triton's proximity to Earth, and with the help of adaptive optics, we can resolve the object and the two stellar images. So if the atmosphere isn't spherical, the center of the curvature of the limb won't be at the center of the object. So it follows an evolute, such as this one. In this case, the atmosphere has an elliptic shape that is exaggerated, so we can see it better. And the evolute that it causes is a diamond shape curve. A shape like this can cause a discontinuous increase that the observers can record as well. So let's talk about Triton. Triton is the largest of Neptune's satellites with a radius of 1,353 kilometers. It's the only satellite in the solar system besides Triton to possess a significant atmosphere. Its atmosphere is mainly composed of molecular nitrogen that is in vapor pressure equilibrium with the molecular nitrogen frost at the surface. Voyager 2 probed the atmosphere during its flyby in 1989, and it provided a surface pressure of 14 microbar, and that gives an estimation of a surface at a temperature of about 40 Kelvin. And it's also potential ocean world, and there's some spacecraft missions being proposed to explore the Neptunian system, and in particular Triton. But other than that, why is it important to study Triton, and in particular its atmosphere? So we are currently coming out of the extreme southern solstice of 2000, where latitudes up to 50 degrees south were directly and constantly illuminated by the sun. And this only occurs about every 650 years. This is because of a combination of Neptune's heliocentric motion and Triton's orbital precession. So now would be the best time to do observations on Triton in order to answer the question, did Triton's atmospheric pressure change during this extreme solstice. So the last observation is roughly symmetrical to the observation made by Voyager's Flyby. And also shown here are other Earth-based observations. They're all occultations, just so we could be consistent in the method used. Okay, so now I'll talk about the observations of the 2017 event. And prediction of this occultation event of October 5th, 2017 was shared with potential observers. This prediction featured a star that smaller telescopes could observe, and it was passing over Europe, Eastern USA, and Northern Africa. The Gaia mission also provided a preliminary release of the DR2 catalog. It had over 400 stars in Triton's field of view, and that allowed for the improvement of the astrometry, and it gave this final prediction. And there were 90 positive observations reported. So most were in Europe, a handful in Eastern USA, and another in Northern Africa. So this is Triton's shadow path for the event. The white line is the predicted path, and the blue line here and here are the effective path. So the prediction with Gaia is very close to the post-diction, so to within 12 kilometers. This black line here is centrality, and the black dots are spaced by 1 minute, and the arrow indicates the direction of motion. The different colored dots are all the stations. Blue is the stations that had a successful observation and were used in the FIT. Red, successful observation but not used in the FIT. And the white stations attempted an observation but were otherwise clouded out or had technical difficulties. Also, Gaia made a press release regarding these observations. So now I have a closer look at the central flash path. The lines here correspond to a spacing of 50 kilometers projected in the sky plane. And I will show the light curve here. It's the closest to centrality that has the best signal to noise ratio. And so here we have Neptune, and we have the star plus Triton, and right at the start of the event. And as we get closer to the middle of the event, we see the increase of flux. And this central flash and the other central flashes provide information about the deepest layers of Triton's atmosphere. So in this case, it says that it's spherical or very close to spherical. So I show you here the occultation chords for all stations. They span Triton almost top to bottom, covered both summer and winter hemispheres, morning and evening limbs. Again, the blue lines are stations used in the FIT, and red are the ones that aren't used in the FIT. So now, moving on to the results obtained. So I'll talk about the methodology here a bit. First, I use the bootstrap method without considering the central flashes to retrieve the molecular density, the pressure, and the temperature profiles. So I do that by using Abel inversions, and I'll show them in a minute. And that gives the density profiles, and then I can derive the pressure and the temperature profiles using the hydrostatic and ideal gas laws. So then I use a direct approach, and that's simply, I take the resulting profiles, I smooth and parametrize them according to physical arguments. And then finally, I use a ray tracing approach to generate a synthetic light curve, and that is fitted to all the other occultation light curves. And one product of that is the location of Triton's center, and that is used iteratively, hence the bootstrap, with the Abel inversion, and that improves the accuracy of the altitude scale. And then finally, the other method that is used is the central flash fitting, and that is used to measure any departure from a spherical shape in the deep atmosphere. It can eventually also be used to constrain its wind regime or reveal possible absorbing material like hazes and clouds. So to summarize the assumptions that are used so that I can use this bootstrap method, the atmosphere is composed of pure molecular nitrogen, methane, that the next most abundant molecule, has a mixing ratio of less than 10 to the -3, and that is negligible for refractive occultations. The atmosphere is transparent, and the upper atmosphere is globally spherical. And at the end, I will discuss the validity of these two assumptions. So the first thing to do to employ the Abel inversion is to assess Triton's contribution to the total flux of the light curve. So, and for that, I use this first equation. The subscript T is Triton and S is the occulted star. So we do this by using calibration images, and those are images that are taken when Triton and the occulted star are angularly separated. So they're both resolved. So this first equation gives the phi0, which is the intruding Triton flux in the light curves. And the second equation, we use it to measure the terms on the left in the calibration images. So when they're separated, and the term here on the right in the occultation images. And if they're not equal to each other, that can reveal intrinsic problems with the calibration images. And here the R refers to a reference star or object. So this light curve from La Palma was the first to be used in the Abel inversion. And that is because it's the best in terms of signal to noise ratio, has good calibration images, and it's also far enough from centrality so that the light curve is mostly determined by the primary image. And here the black dots are the data. The blue line is the synthetic model derived from the direct approach, and the green are the residuals. So despite this, finding the phi0 for this light curve was challenging. But I'll talk about that after this. So I'll first show two other light curves that were used. So because it was a challenge to find phi0, we decided to find other light curves that could be used to do the Abel inversion. In the case of Helmholtz, it has the same characteristics as La Palma. So it has a high signal to noise ratio, good calibration images, and is far from centrality. And so it was used in conjunction with La Palma. And then for shape confirmation purposes, I used the Calern station. In this case, the central flash had to be removed because it's influenced by the secondary image. And I used a phi0 that was determined by the model obtained previously using the other two light curves inversion, because there are no calibration images from this station. Okay, so varying phi0 changes mostly the deepest parts of the temperature profile shown here. It changes only the flash, the central flash layer, so it doesn't affect light curves without this feature. So that's why it was a challenge to find La Palma's phi0, because it gave a baseline that it was too large. It gave this rightmost line here. And La Palma and Helmholtz's phi0, they were mutually inconsistent with each other. And we realized it was a problem with La Palma's inversion because this template temperature model provided a model where the central flashes were too narrow to fit the data. So After some fitting, I came to the conclusion that the best phi 0 for La Palma was this one, 0.3885, 35885. And that finally explains the central flashes. And that is this template model, the thicker template model here. And it has these characteristics in this table here. So this general positive gradient in the upper part is a result of choice of initial conditions. This is intended to match the temperature profiles obtained by Strobel and Zhu in 2017. But regardless, above 1,450 kilometers, about the altitude imposed in the initial condition, the inversion doesn't have much more information from the light curves because it's too close to the beginning and the end of the event. So that causes the inversion to not give any relevant information above that point. And also, as a note, the data doesn't reach the surface. So the surface temperature of 38 Kelvin is also a choice that we made. It can be changed a bit and it doesn't affect the fit. Okay, so also as a note, the inversions now fit independent observations of carbon monoxide from ALMA. And it's shown here in black and superimposed with the inversion from La Palma and Helmholtz. So the temperature profile, the temperature model that we obtained produces this synthetic light curve. The green light curve represents the flux with only one stellar image, and the black curve is the sum of the green curve and its mirrored version. This curve is used to fit the observations using the ray tracing that I'll talk about shortly. First, just want to show the main result from the Abel inversion, but here I present the paths of the primary, which is the red dots, and the secondary blue dots of the stellar images above Triton's surface, and this is seen from a centermost station. So these arrows indicate the direction of these stellar images path, and all stations probed the same path or part of it, and the primary and secondary images are swapped if the station probed south of the shadow center. So here the stars indicate egress at half light level, and the diamonds indicate the other way around. Yes, stars indicate ingress and diamonds indicate egress at the half light level. So the three stations that were used in the inversion probed south of the shadow center. So, okay, so now I show the results of the Abel inversion. This is the result for the molecular density in relation to the satellite radius. And so here the black line is Triton's surface. We can see that all three inversions match well with each other, and that shows that the three stations probed essentially identical atmospheric layers. And I will comment on this gray line from Calern in the next slide. I will discuss in a bit how I obtained this green Voyager 2 line, and then this thin black line is this the template model. So here is the temperature profile from the three inversions. All of the retrieved temperature profiles show a turning point in their deepest parts, so where the temperature gradient becomes negative. So now the gray lines, the Calern is noisier than the other two light curves that we used here, and that makes it not as good, but we do see the same trend, and that's all I wanted to know about to do this inversion. So, and there also may have the there also may be some systematic effects caused by Calern's phi-0. So now with the smoothed profile, I can do the ray tracing approach. So I fit the synthetic profile to all light curves. So here's an example of 6 of them. I used 52 of the set of 90 using the light curves with a better signal to noise ratio. And with that sample, I can do a chi-square map. So this plot shows the pressure at 1400 kilometers and the correction of the transverse of the JPL ephemerides. The inner gray line is the contour at the 1 sigma limit, and the outer one is the 3 sigma limit. The goal of this fit was to get the global properties of the atmosphere, and so in particular to constrain the pressure at 1400 kilometers and the location of the shadow center with respect to the occultation quartz. So then I can refeed the shadow center into the Abel inversion to refine the iteration. And that final result provides a satisfactory fit. So we have 54 fitted parameters and almost 70,000 data points. And that gives a value of the chi-square per degree of freedom of 0.85. And that gives a pressure at 1400 kilometers of 1.18 microbar. So now I have here the data from Voyager 2's radio science experiments during the flyby of the Neptunian system. In this case, the occultation object was the spacecraft itself, and it was sending a radio signal back to Earth as it passed behind Triton. Because of that, as we saw in the beginning, the main result was the surface pressure. But even though it's quite noisy above about 20 kilometers altitude, it's still possible to extract some information from the experiment. So the raw data, which is here represented by these black crosses in the first plot, is a radio phase related to 2 radio signals at 3.6 and 13 centimeters. And they are the X and the S band, respectively. So this delta phi is the corrected radio phase that corresponds to the neutral atmosphere at the X band wavelength, so at the 3.6. This calculation here is done to remove plasma effects on the phase. And then the B1, B2, and B3 in the first plot are polynomials that are used to obtain the pure atmosphere, eliminating instabilities in the frequency reference of the spacecraft. So in the original analysis in 1995, Gurola gave the B2, which is a second order polynomial, as the preferred polynomial. And so I use it in the second plot to compare the data, to compare the Voyager 2 data. And in order to compare these results to ours, I generated the phase delay at 3.6 centimeters that would be observed without profiles, as if they were on board of Voyager. And that we can do using this equation, the second equation, where lambda is the wavelength of 3.6 centimeters. K is the molecular refractivity of molecular nitrogen, and this sigma here is the column density from our template model. So our template model is also shown in the second plot in this black line here, and this red line represents all the light curves that were inverted because there's no real difference here between all of them. And like I said, green is Voyager's results. The smooth line is a model from Gurola. So on the other hand, I used Voyager's radio phase to retrieve the refractivity profile using this Abel inversion. And then I can obtain the density profile. So now I can compare our results directly to Voyager's. So here, I showed the data minus each of the polynomials, as well as Gurola's model. So they're all in green. The other colorful lines are the results of our light curves inversions. And the thin black line, again, is our best model. So I stopped the Voyager profile around 1400 kilometers, because above that, it becomes too noisy to be reliable. And what we can see is that the profile probes altitudes that overlap with our own. So this whole part here. And it shows that there is no significant difference in density between 1989 and the 2017 profiles. And it also shows that the Voyager density profile is insensitive to the choice of polynomial. So integrating the weights of the atmospheric column provides the Voyager pressure profile. But here the profile includes a contribution of the weight of all the layers above 1400 kilometers, where Voyager's data is very noisy. So here the polynomial B1 is very offset in slope compared to B2 and B3. But Gurola discarded this first polynomial, this polynomial in particular, because it's a linear polynomial, and it was determined using only up to 120 kilometers of the data. And he considered that insufficient to estimate the drift of the instrument over the atmosphere. On the other hand, B2 and B3 used about 700 kilometers of the data, and they match rather nicely in phase delay, density, and pressure profiles. But because this slope is sensitive to the choice of the baseline polynomial, it's difficult to conclude if the break in the slope between the Voyager profile and our ground-based results is real or not. So the conclusion that can be reached from the pressure profile of Voyagers is the difference of pressure between the surface and the lowest point of the La Palma profile, which is at 1373 kilometers, and that is 9.82 microbar. Because of that, I decided to do a different approach to estimate the surface pressure for Voyager. So with that, I used independent measurements of the surface temperature from the literature. The different values are shown here in these colored rectangles. From these surface pressures, we can estimate the surface pressure of about 12.5 microbar, which is consistent with Gurola's result of 14 microbar with an error of plus or minus 2. We also estimate a conservative range for the pressure at 1400 kilometers of 1 microbar. When compared to the result from 2017, that is 1.18 microbars, we don't see significant variations of the pressure between the two sets of data. So it's important to note that it was still possible to extract new information from the Voyager experiment, even after the science was considered exhausted. And this result was crucial for the work because we can compare it directly, and it shows that the Triton's atmospheric pressure in 2017 is back to the levels of Voyager 2. So I'll talk briefly about two other observations, occultations obtained. So this first one from the 18th of July, 1995, was a joint effort between two groups involving 4 stations. And for this work, I reanalyze the data using our approach. So I adopt the same temperature profile as for 2017, but vary the pressure at 1400 kilometers to fit the synthetic light curves to the data. I do the same here for the second event of the 21st of May 2008. It also involved 4 stations, but here each pair of stations is very close to each other. So only 2 effective chords were obtained, and they were also grazing. So there is a strong correlation between the closest approach and the retrieved pressure. So because of that, the value of the pressure is very poorly constrained. So now I'll put these results into context. So I show here the values of the pressure at 1400 kilometers for the different occultations that were done since 1989, both from this work and from other works. This extrapolation shown here, it stems from the template model, and it's down to the surface, and that is used to calculate the other surface pressures that are in parentheses. So let's analyze the plot now. For the pressure at 1400 kilometers over the years. So the red points is from this analysis, blue is from other works. So starting at the point from 95, it indicates a 40% increase of pressure at a significant level of 1.8 sigma. So then in 1997, in the 18th of July, there are 2 values. So they are derived from the same event, but different teams. And these results are shown in Elliott et al. 2000. So the difference between them comes from a different template model used. And they remain at the 0.6 sigma level between each other. So that's not statistically significant. So using our value, we get a pressure increase at the 2.5 sigma level. The 2008 event provided only 2 grazing events, and it brings no new information, and no conclusion can be inferred for that year. I'll go back in time now. So the 4th of November, 1997, has a low error bar because of the high signal to noise ratio of the light curve, which was obtained with the Hubble Space Telescope. This value, it gives an increase of pressure at the 3.8 sigma level, but it's not clear how astrometry was done because it's a single chord event, and I don't have access to that data yet, so I can't verify the results using this my methods to confirm the increase. But in any case, the value obtained in 2017, again, the error bars are smaller than the diamond, is fully compatible with the one obtained from Voyager, and it falls well within the 3 sigma level. So what I can say for certain is, so either no surge occurred between 1989 and 2017, or if it happened, the pressure is back to its Voyager level. So here I showed the surface pressure on Triton over the years simulated by Bertrand and et al. 2021 using their volatile transport model. The blue lines refer to a southern cap that extends up to the equator, and the pink lines are a southern cap that extends only up to 30 degrees south. And then each line represents different extensions of the northern cap. In these simulations, the surface pressure peak occurs slightly after the extreme solstice. It seems that a southern cap extending up to the equator is necessary so that the surface pressure falls closer to the 2017 value as shown here. Also, these results suggest that a northern polar cap that extends down to at least 45 to 60 degrees north is needed in 2017 to make sure that the surface pressure is at 14 microbar. So that is back at the Voyager 2 level. If there is no northern cap, then the pressure is higher than 16 microbar in 2017, and that's inconsistent with our observations. And as a note, so the presence of a permanent southern and northern cap prevents Triton's atmosphere from collapsing, according to the model. So now let's talk a bit about the central flash analysis. Among the 52 light curves used, I used 20 for the central flash modeling. So I have here an expected intensity map of Triton's shadow. There's this bright dot near the center. It corresponds to the central flash. The direction of Triton's rotation is shown, and the equatorial rotation velocity as well of 17 meters per second. So even though the Abel inversion method isn't valid for central flash analysis because of the secondary image, the ray tracing allows for that because it includes both images in the code. The central flash then allows us to gain about 12 kilometers down, and that corresponds to about 8 kilometers altitude compared to the inversion method. And while I ignored the central flash in the ray tracing approach before, I now include it, and I now allow for the departure from sphericity of the layer responsible for the central flash. So the quality of the fit is now 0.80, and that's comparable to what was obtained without the flashes. That was 0.85. And that shows that there's no detectable departure from sphericity. There's also another argument to support that. The center of Triton's shadow, determined by the fit to all flashes and excluding the ingress and egress parts, it coincides to within 0.1 kilometers with the shadow center of the global fit. And that offset isn't significant, considering the global fit has a 1 sigma error of about 1 kilometer. So now to talk about the ablateness a bit, it's defined by this approximation here, where the apparent ablateness is used with this A prime is the apparent semi-major axis, and B prime is the apparent semi-minor axis, and the capital B is the sub-observer latitude. The center of curvature of that ellipse causes a diamond-shaped caustic curve, like this one here. So I explored different values for the apparent ablateness, starting at 0. And for this study, only 5 stations were considered, and they are shown here. All the others are too far to discern any deviation from sphericity. So they are not used here. So I arrive at an ablateness upper limit of 0.0019 for our data. And this is the central flash intensity map for that value. And that corresponds to a difference between the equatorial and polar radii of about 3 kilometers. So here, we assume that the central flash layer shape is entirely supported by zonal winds. So using the equatorial, so this VE as the equatorial velocity for the zonal wind in a rotating frame with Triton at the 8 kilometer altitude, So using the 17 meters per second as rotation, as Triton's equatorial rotation, I obtained these upper limits for the retrogrades and the prograde when at the 1 sigma level. But global retrograde winds weren't observed by Voyager. So to obtain a prograde rotation in the mid-southern latitudes, because of the observations of the plumes, the interhemispheric condensation has to be weak. But it's possible to have a super rotation that could explain the direction of the plumes. And this value, this upper limit, is a constraint for this hypothetical super rotation. It's also worth noting that these velocity results are higher than what is predicted by circulation models. So this result can't constrain them. So I went searching for other results in the literature, and one of them is shown here. Is from Elliott et al. 1997, from the Occultation of 1995. The closest approach from the shadow center was about 100 kilometers, which is outside the caustic, meaning that the observation couldn't confirm this evolute. But this shape would cause strong flux variation in our data set, and they were not observed. So this oblateness is inconsistent with our observations. That would also require unrealistic high velocities, high wind velocities, for the atmosphere to be able to maintain these strong distortions. They would have to be supersonic. So I think that the differences between the flash models and this observation from 95 would be caused by small local corrugations of the flash layer that can be induced by gravity waves. So throughout this work, I assume that Triton's atmosphere is clear, transparent, and free of absorbing material. But Voyager 2's observations revealed hazes and clouds in the lower atmosphere, and they are two types of absorbing features. So, absorbing material should be detected best in the central flash structures that are caused by a layer at around 8 kilometers altitude because of their lower altitudes, and because the central flash probes down to that altitude level. So the slant optical depth, so that is the optical depth along the line of sight for hazes, is given with this relation at the top, and that means that the hazes are expected to cause a reduction of the central flash of 5 to 10% if there's no changes since 1989. And for clouds that are more denser than hazes, the relation at the bottom tells us that the clouds should decrease the central flash amplitude by a factor of 4 or more. But I don't see any departure from the template temperature model that is assumed as spherical on the highest central flash observations from the 2017 event. And also, I don't see any trends on the observed central flash amplitudes regarding different wavelengths. So that these results seem to show that hazes and clouds have no detectable effects on our central flash shapes. So meaning that our template temperature model is consistent to explain all observations, including the central flashes, using a clear, transparent atmosphere. But the height of the central flash actually depends on the assumed template temperature model. So to separate the haze from the temperature effects, independent information on the temperature profile of the lower atmosphere is needed. So using the ALMA observations of carbon monoxide again, we see that our template temperature model should be sound because it's consistent with independent observations. So some final points to include now are, the results from my work and also the results shown here are also in a future paper with the Astronomy and Astrophysics Journal. It's currently under revision. So after some first moderate remarks by the referees, there will be an occultation on the 6th of October 2022. There will be another occultation by Triton, and it's the first since 2017. The path is expected to cross most of Asia, and this will be important to add one more data point in the atmospheric pressure evolution of the satellite. So, and I will finish by leaving you with the conclusions up. So, thank you.
Thank you very much, Joana. Perfect timing. So we are right away switching to the discussion part and with questions. I will first give the opportunity for our rapporteur, and I will start with Dr. Candice Hansen. Candice, as you probably know, the tradition is you first give your opinion on the work and the thesis, and then you can ask a question.
So I was very pleased with the dissertation itself. Is very comprehensive and goes into a lot of detail on the techniques. I feel like the conclusions that are drawn from the data analysis are well supported by the analysis that was done. I think that when I was reviewing the dissertation itself, I felt like there was perhaps a little more emphasis on the modeling as being sort of the modeling is right and do our data fit, where realistically it should be the other way around. Here's our data and how do the models reproduce our data? So that was one thing that I thought could be improved a bit. The other thing that I haven't really heard much about is the difference, if there really was a difference on ingress and egress, and how that might relate to the data itself, as when you consider what was going on Triton. So, the path took. I mean, the star was on the ingress, I believe, over the South Polar terrain, on the egress over the Cantaloupe terrain, and how did that affect things, possibly? And then the other item to bring up would be the last one about hazes and clouds. And I mean, Voyager did see hazes and clouds, of course, but is it possible that they've simply dissipated and the atmosphere is in fact clear now? And what does that say about the climate itself?
Okay, so just to say first from the ingress and egress, so we don't see any differences in the light curves between the ingress and egress. So yeah, so that's why we didn't do any special study there.
Okay.
We don't see anything, any difference. And the other question was about the hazes and the clouds, and if they could be cleared now. Yes. Yes, it's I mean, it could be a possibility to, because we don't see any. That could be a possibility, and maybe it could be explained from the southern solstice, but I didn't go into much detail about that, so I can't say for sure if that was absolutely what could have occurred.
Okay. I mean, I think that's really quite a fascinating result. That, maybe you'll take up next.
Andy, you can ask more questions if you want.
Oh, okay.
Yeah, you have the floor for several questions. We have some time. It's an important part of the defense.
Okay. Excuse me. Another thing that if you could explain to me, I mean, the light curves go all the way to the surface. Why is it that you cannot actually analyze the data below 8 kilometers?
No, they don't reach the data, the surface, sorry. The deepest that they could probe is the 8 kilometers. So the centralmost station probed at 8 kilometers altitude. It doesn't reach the surface.
Maybe you can
yeah,
describe
that's the part
physical
I'm
process.
Yeah, no, that's the part I'm confused about, because I mean the star went behind the limb, and so that lower 8 kilometers, if it's not blocked by haze, is it because of the confusion of the central flash that it becomes quite ambiguous?
Joana, you can go ahead and re-explain the refraction and quickly to make things clear. We can see how. Well, not using your slide. You can use your slide. Welcome. Okay.
So it is basically the confusion of all those rays overlapping each other. But then in that case, why can't you use the ones that are further from the center point?
These ones right here. These ones?
Well, those would be higher in the atmosphere, of course. I mean, this chart makes your argument for why they're higher in the higher data is okay. So I think I'm really just wanting you to agree with me that I'm saying the data itself becomes sort of not possible to disentangle as you get lower in the atmosphere.
Yeah, yes, I'd say that's why, and also I believe that the atmosphere is dense enough that it wouldn't be able to reach the surface.
Okay. Okay. The next question that I had, and I was hoping that you would have a new graphic for this, is you have derived the different thermal gradients in different portions of the atmosphere. Oh, actually, I think I did see a slide on that. But can you go back to that one, please?
This
one? Yeah, that would work. So what can you tell me about what's going on? So first it's cooling from the surface working up, which makes sense. So what is the mechanism? Or I'm sorry, why don't you walk me through what's going on here?
Okay. So I'll start from the surface. So from the surface, there's an increase of 5 kilometers, Kelvin per kilometers gradient. And then there is an elbow at the that would be the indication of the mesosphere here, yes, and which gives another inversion, and it cools down again, and then there is an increase. So this increase, so we did some studies of methane, and we saw that we could reach it. So we asked Daryl to see if, with his models from Strobel and Zhu in 2017, if it was possible for the amount of CH4 to do this increase, and he found that yes, it's possible to have this strong increase without increasing the pressure globally, because the methane and molecular nitrogen are not well mixed in the ice. So they can be decoupled, and so that could give this very steep increase. This very steep increase from the surface up to our peak of the lower atmosphere. So then we see this hint of the mesosphere, which I forget the year, but I know that Elliott et al. Also saw this mesosphere in another occultation. And then we see again the increase for the thermosphere closer to the edge of the atmosphere.
Okay. So the 38 Kelvin is, of course, pinned by the temperature of the ice, but not all of the surface is presumably covered by ice. And so does that change things if you have a patch of surface that's warm and you have the patch of frost that's pinned at the vapor pressure equilibrium point? Does that help?
That could change locally only. So what we see for the most part would be this, that this would explain the data more up to the 8 kilometer. But again, we can't see below around here. So all of this, we can't get information. So it could go to 38, or it could go to a warmer point where there's no ice and we wouldn't be able to see it.
Okay.
Okay, thank you, Candy. Are you? Thank you very much. Then we can give the floor to the other rapporteur, Pascal Ranou.
Okay, thank you for this presentation. In fact, I found it very clear, especially because I'm not very used to occultation. Then I really follow it very well. And I have many questions, but I will start with a question which is not about science, but about organization and management. Because apparently there was 90 observations made around the world, and you have written that it was complicated to get back the data, or sometimes you have the data but not all the information related to the data, and in some cases you have not used this data. And could you tell us why it was difficult? And what could be improved to change that for the next observations?
Sure. So in some cases, so there were about 200 observers around that, and some gave the information. So the information about the stations, like the coordinates of the station, what camera they used, and all the information that needed to be used for the analysis. And they also provided the data. some did that immediately. Others didn't do that. They gave the report, but they didn't give the data, or they didn't give any light curve. They just said it was positive. So we had to track them down, and I had to write emails to them, and sometimes they wouldn't reply, and so I had to send again.
I understand, but what makes what's happened for them not to give all, because the purpose was to make an observation and to give the information to be analyzed. Then what's in your mind, what's happened and what could be changed for the future? Because you said about another occultation next year.
I don't know what happened.
No.
Maybe it's.
I agree. It's not science. It's management.
Yes, but maybe to improve, it would be easier to have an online not repository, a place to just put the data so that it could be uploaded immediately to the researchers. So it could be, so that it wouldn't be most of them. It had to be. Some had to be sent over with a USB drive. Others, it was over with a, what's it called, the Google Drive. But some people don't have a very big Google Drive, so I think that also played a part of it. The finding the way to transfer gigabytes of data to us.
It's a lot of data, in fact. Okay.
Yes. Some of them had 13 gigabytes.
Okay. And when you are in a remote place, it can be difficult. After, there was 90 observations that was usable, apparently. And why this has not been analyzed by one person to really be sure that the treatment is homogeneous? Because if you have analyzed 18 of them, 45 were done by people of the Lucky Star team, and the other by the observer. How do you manage to be certain that to be sure that the analysis is conform in each case?
So for most of them, I know the software that was used. And almost all of them, except for maybe one or two observers, was done by professional researchers. So, and it ended up also being time constraints, because 18, I was taking too long already.
Yes.
And it would be me just doing the whole thing for 4 years.
Okay, it was my other question is how much time it takes to make the analysis of one observation, because I was not clear about that. You said it's a long process, right? Yes.
For some, it could take 1 day. For others, it could take a week. It depends highly on how the quality of the data, and if the software can pick up the image, or if it loses it, and then some fitting has to be done, and there's a lot of fine tuning to the program that depends a lot on each light curve.
Okay, then yes, then 90 observation is too much for one person only to do it in a reasonable time. That's the point. Okay. In fact, well, but then the other question behind is then you have to absolutely trust the way the process was done, because if you have because even if it's made by professional, you know that if there is many procedure, you can have some difference. It's something very common between different procedure. You can have a difference in analysis, and then after you have gathering everything to make a common analysis of the results. And do you have a way to cross-check the analysis? Maybe, for instance, to make some analysis of some observation by several persons to check that it is consistent? Or did you have another procedure to that?
Yes. So I had some of the observations were done redundantly. So some were made by one member of the Lucky Star team, and other were in the same light curve was analyzed also by me, so that we could see if there's any big difference. And for the most part, the light curves that were given to us by the observers directly, that we just further improved. Most of them weren't used in the fit. They were used only to show that it fits, that the synthetic light curve fits that observation.
Okay, I see. You have plenty of observation made at different latitude, and you use only one template model for the temperature. But at some point, I was wondering why you cannot make a map of temperature, because the template temperature is meant to have a global analysis of the observation with the center flash. But after, I guess that you can be more fine, do a more specific work to have, for instance, a latitude profile of temperature. Is this possible or not? I was expecting, for instance, to have a map of temperature as a function of the latitude with this kind of data.
To be able to have that data, I would have to do enable inversion to all the light curves. And like I said, it needs to have good signal to noise ratio, and it needs good calibration images. And so it's quite
it's simply
procedure. Yeah, it's not as simple. I mean, come on, where is it? It's here. So two of the stations are from the two southernmost light curves that we have, and then Calern is one of the centermost, and the profile is still consistent, even though the Calern is noisier. But that's also why I used Calern, just to confirm the shape. And that's why also I used one that was closer to centrality, just to see if there would be any difference in the temperature.
But what you say is that the other profiles are not usable to get an accurate temperature profile at other latitudes. That's what you say, in fact.
They're not as easy to use because of the lack of calibration images. And
okay.
Yeah.
Okay, then only a few could be done. It's not enough to make a complete map. That's okay. In fact, in the manuscript, and now at the oral, I feel that you don't believe the pressure surge during the year the 90s. And is what I wrote in my report is that you have the Voyager point, the Voyager pressure value. You have an increased resonancy with two observations which were completely independent, and then a decrease. And even today, I feel you were skeptical about that, and I would like to know why. Because if I see this figure, if there was only the point of 97, I could say, well, there is many uncertainties. But you have also the observation of 95, which gives strength to this increase of pressure.
So I think that the biggest point here would be this this blue one from November 97. That would that is at the 3.8 sigma level. But the problem with it, it's that it's only one single chord event, and so I've been talking to this team. I've been talking to Mike Person, so I could have access to the data so that we could use this method to just confirm the increase, because that is something that I want to do. I want to make sure that did it actually happen or did it not. So I'm on the I'm not skeptical. I'm on the fence, if that could be.
But you always speak about the 1907 observation, but the 95 observation also show an increase, and the pressure in 90, 95, and 97 show a trend which looks real.
So
it's my question. I don't know. Maybe. I have I look this naively. It's a curve. I say, okay, there is a trend. It's well beyond the error bars, and I feel that you don't believe that. I would like to know why.
So for this, I prefer using a 3 sigma, above 3 sigma to be the significant, and this one is 1.8, and this one would be 2.5. So
if I may, it's true that so it's a kind of perspective, but it's true that it will be nice to. Of course, there is only one chord for the November 1997 occultation, but it's from Hubble, as you know.
Mm-hmm.
I noticed also, maybe it's incautious, you do not cite this occultation was published in a Nature paper by Elliott et al., and you don't even cite it. So it's you cite later papers, but it was a big paper, Global Warming on Triton. I think it was an important, so I think it's revealing that you indeed, we all dream of you and people from the Lucky Star team to look at these the original data if needed, to maybe also process the treatment at the time was certainly, I think Cathy was in the team, but if to be sure that it's homogeneous, of course, we all look forward to see the treatment of this curve by with your tools and see if it's consistent. Okay, I take advantage of being
so we don't cite that one because there was a later analysis with that light curve.
Yeah,
using the Abel inversion, and so we use that one.
Okay.
Yeah, so that's why the Nature one, I think, isn't cited. We cited the later one with the
absolutely.
With the one that used the inversion, because that would be even more to be able to compare to, because it's an Abel inversion.
But it's rare in astrophysics to have people wanted to have a 3 sigma error bars to trust something. In general, with 1 sigma error bar, we are generally quite happy. Then, okay, I know that. In fact, even this curve can be modeled by GCMs. Of course, you have to make special limit condition to the GCM to get this, but it's not impossible. That's the point in any case. Okay. Now, well, we are going back to. Sorry to the haze. You know, I'm working on haze, and it's my hobby. And you all your analysis start with the hypothesis that the atmosphere is transparent, which is okay. To start, it makes sense. But I would like to know if you have an idea of how if you have included haze in your model, what will be the effect on the analysis And moreover, is it possible, if is what is written in page 100, you refer to, I think it was to Elliot, that the central flash could be modified by the presence of haze. I don't see how it could happen, but for instance, would it be possible to convert oblateness in haze opacity, for instance, in the model?
So, here?
Yes, for instance, you are looking at small oblateness of the caustic of the central flash, but is it possible to explain the same thing with a haze layer, or even eventually not uniform haze layer? In the page 100 of your manuscript, there is a very small paragraph that says that I think it was for Elliot that was proposing that yes, this kind of this flash could be due to haze rather than to winds. I don't know. I don't understand how it could. What would be the mechanism? But that means that if the atmosphere was not transparent at the initial step, it could be due to haze. It's a question. I don't know the answer.
So I'm not sure if I understood it completely. But I'll start saying that haze would be more determinant in the central flash layer, and that would cause a dampening. So it would be the amplitude of the flash would be lower than what we saw, and that would because that is because the absorption would start to be a factor there.
Yeah, I understand that the haze could decrease the flash, but is it possible that the haze layer, especially if it's not uniform, could change the shape of the central flash, which looks to be something possible as you have written on the manuscript?
Yes, it could change the shape if yes.
And then the counterpart is what's happened if you don't assume that the atmosphere is transparent. In fact, you cannot find haze only. You don't find haze only because of the central flash, which is not dim. There is no chromatic effect. That's your point. But you may have haze without chromatic effects if the particle has large genus, for instance. And that could produce a modification of the flash.
Yes, in general, yes.
Yes.
But we didn't have a lot of observations with different wavelengths, but we do have some stations that are close to each other, and they have different wavelengths, and there's no difference there's no effects noticeable from the chromatic effects that would be caused by the hazes.
Yes. Well, okay, I understand. The chromatic effect is only produced with quite small particles. If you have bigger particle, maybe you wouldn't have a chromatic effect. But in fact, if you wanted to do in the future, for instance, you could reanalyze that, having in mind that the atmosphere is not transparent. That would be possible eventually.
Yes, absolutely.
Okay. Okay.
And we could even use some of your models.
Yes, sure. But I wait for this paper then. Yes, and in fact, I wanted just to note something. You refer to the cloud layer, and I went back to the paper of Regis, but the cloud layer is below 8 kilometers. then in principle, with your observation, even if there was a cloud layer, you won't be able to probe it. Then
they would be right at the.
Yes. Then in fact, what you can say for sure is that you don't see haze, but a cloud layer could be somewhere between 0 and 5 kilometers, and you will not see it in fact. And just two last comments, and one comment and one question. In fact, I found very interesting all the way you have to describe the treatment of the caustic, because you made that with approximation, and this is something that we can follow in principle with calculation, because in fact you made all the calculation which are in principle tractable, that you can follow, and you can make the analytical calculation. But sometimes I found that quite difficult, because there is some steps that are missing, and maybe I would suggest to make it more clear for the reader, because it is very useful to have this kind of arguments to explain in a very simple way, an analytical way, something which is complicated. And I'm going to ask a last question, which is a little bit a provocation, but I'm sure you will understand. During decades, there was many occultation of Pluto, which gave a vertical profile of pressure and temperature, and especially for the temperature, it was giving all the occultation was giving a given type of temperature, and finally, when New Horizon came, the vertical profile of temperature was very surprising, because it was not expected from occultation. And I would like to know what was learned from this to the new analysis of Triton of Pluto, because we know that this kind of analysis may be wrong in some way, and in what it was useful to see the difference between the former occultation of Pluto and the reality found described by New Horizon.
First, Bruno, correct me if I'm wrong. I think an occultation did see the Mesosphere in Pluto, right?
Yeah, if I may step in. Well, New Horizon confirmed the ground-based condition.
It was observed before.
Yeah. It was, if you look at the Hinson and Tal paper on the Rex radio experiment, the main conclusion is that ground-based occultation basically grasped the Pluto's temperature, density, and pressure profiles.
Bruno cannot say it, but I think New Horizon was a triumph for stellar occultation.
Okay. In fact, well, because when I saw the result, I was surprised, because I thought nobody have seen it, but maybe I probably didn't read all the literature about Pluto.
And I can chime in, but Daryl might be better suited as well. I believe what's being asked about is the ultraviolet occultation, the solar occultation, which is probing a very different part of the atmosphere than the stellar occultations. I agree with what Francois and Bruno are saying, that the New Horizons results confirmed the stellar occultations, but we did have a surprise from the UV solar occultation on the very upper atmosphere. Yeah. So I think that is the crux of the question. And of course, Daryl is very much an expert on that. So.
I don't know, can you hear me?
Yes.
I'm finished. Thank you.
I mean, I can just comment, basically, the boundary condition that the stellar occultation that Bruno had was at 80 degrees Kelvin. And if he had used 70 degrees, it'd be much closer. I cross-compared the stellar occultation against the radio occultation at below 1,300 kilometers. And I basically find there's a difference of, I forget which is which, but 13% for one in between densities and 20% between pressures. The biggest difference is near the ground level, the last, let's say, 20, 25 kilometers between radio occultation and the stellar.
Okay, thank you, Pascal. We can move on to the comments from the examiner, starting with Kathy Olkin. So comments and a couple of questions. Thank you.
Sure. Joanna, very nice work here. That was a lot of light curves to manage. I can only imagine the challenges getting everyone to get you data, and then to go through the process of overlaying your results and fitting your results for different data sets. I also really appreciated that you went back to the Voyager 2 radio science experiment and did a reanalysis of that. I have a couple of questions in the similar vein of ones that you've heard previously, because hazes and temporal variation are very interesting things to talk about regarding the work that you've done. So I'll start with my question about hazes. So can you show where haze or geysers were observed on Triton relative to where the occultations probed? So you have that nice map of Triton, and speak to maybe the spatial area that was probed versus the idea that hazes could change temporally. Do you have any, what I'm asking really is, do you have an idea, if you're not seeing haze, if it could be, can you disentangle whether it's because you're looking at different areas or because something has changed with time?
So actually didn't check where the geysers are in this image, but the hazes aren't don't engulf the atmosphere completely, or not a planet, the satellite completely. So it could very well be that we completely missed them, and this whole path didn't have any hazes, or it could be that something changed. So we can't be sure of which is which.
Okay. Okay. And then I want to ask about the change in temperature, getting back to the 1997 event and that plot that we were looking at just a little bit ago with the different events. So one thing I will say is that there was also a 1993 Triton stellar occultation. It had an atmospheric pressure of, I think, 1.5 plus or minus. The error bars were decently large. So just for your knowledge, and I know that you didn't analyze it, so you can't compare it in the same work. But my question is,
excuse me, which year is it?
1993. It was TR60. There were KAO observations, and I can send you something about it. So yeah, there was one in 1993. First occultation I ever observed. So, just for your own knowledge, I wanted to make sure that you knew that was out there. When I hear, and read what you're saying about the possibility of the increase in pressure at 1,400 kilometers in the mid 1990s. I think it appears to me that one of the reasons that you are not feeling that it's strong, that there strongly was a change in pressure in that time period, is because of some of the modeling that Bertrand did that you showed. You know, because it's also seems inconsistent with this. So my question would be, for thoughts for future work, would be, is there any way to get temperature changes in the mid 1990s that then relax to the Voyager era levels, you know, in 2017? So not really something that I'm, well, do you think that there's any way that that could be done? And I recognize that's a little outside of the work you did, but I would like to have you speculate if you could. Yeah, that's
So,
a big question. Yeah. Yep.
I didn't handle modeling, so I can't really comment on
Okay.
if it could work or not.
Okay, that's fair enough. And I knew that was a little outside of the bounds of the work that you did, but I think it's something to think about for the future. And then one thing I'd like to talk about is the evolute and the elliptical nature of, you know, the oblate or spherical nature of the occultation of the atmosphere. So one thing, in looking at your light curves, you know, you've got this really nice figure of all your light curves in your appendix. Very nice, really appreciated all the pages of this. And could you speak to the fact that the light curve central flashes that you're seeing are pretty much a single central flash, and you don't see two spikes, and how that might inform whether the atmosphere is spherical or oblate? Does that make sense? And if not, I can keep asking.
I think so. The seeing that there's only one spike is what indicates that it's spherical or mostly spherical. So the fact that we don't see the two spikes means that it doesn't go very far from this upper limit that is here for the oblateness. So if it would be something like this, then there would be two spikes, and that would show that the atmosphere isn't spherical. And so that would mean that the model that I showed previously wouldn't be valid, because the atmosphere wouldn't be spherical. But with this smaller oblateness, then it's mostly spherical, and this is even an upper limit. So
right. And so in your modeling, you had to make the evolute small enough so that you couldn't be detecting two spikes, because you didn't observe that in the data.
Yeah.
Yep. Okay. Yeah, that's what I was hoping to hear a clear statement of. So thank you. You know, you hinted at it once early in the presentation, but I think it's a very strong result that you can constrain it, because you only see a single brightening in the middle of your central flashes. And then in the kind of data analysis realm, I know how frustrating it can be to try and normalize a stellar occultation light curve. And you spoke a bit about La Palma and the difficulty you had getting phi 0 for that. Can you speak to, you know, you used Helmos and another site. Can you speak to the wavelength range, the filter used in those different sites? Specifically, I want to know, was the effective wavelength of the observations the same for the data that you used to bootstrap your phi 0 from?
Oh, I don't remember.
Okay.
Uh,
Well, what I'm getting at is that it's critically important that, you know, to normalize the light curve, you have to use data that has the same wavelength, right? Because it's wavelength dependent. So I'm assuming that Helmos and La Palma had similar similar effective wavelengths.
yes, they were, I believe, both visual to near infrared, and Calern was visual. Is that the word visual? I think so. But I believe, yes, I believe that Calern would be the one that is visual. And then the other two, because they're from bigger telescopes, they use the filter. And that was.
You can show the light curve.
Come here. Okay. Oh yeah, it's right in there. I forgot it was right in there.
Oh, okay. Yeah, and I didn't see it when you showed it, so.
So yes, it's
Okay.
720 nanometers, and this is, it's just a bit less, yeah.
Yeah. Okay. And then the last question I have is regarding your Voyager pressure at 1400 kilometers. You have 1.0 plus or minus 0.02 microbars. Can you speak to how you got the 0.02, the error, the uncertainty in that 1400 kilometers, and how it compares? Yeah, basically how you got the error bar. Yeah, right there.
Okay, so this was from this different approach that was done. So I found temperatures in the literature, and then I used the hydrostatic, yes, the ideal gas law, to derive the pressure, and then comparing with the results that we got first from Voyager, and then so we decided to use a conservative range of the error bar at the end, after obtaining the interval from these temperatures, and comparing as well with the initial results that we obtained with Voyager. So before doing this approach with the one that we got here. That wasn't clear.
Yeah, so I'll ask another question. Yeah, so
I'll try to make it more clear. So here, with this, with the B2, that was the preferred solution from Gorola, we got a pressure at the 1400s. But because of the difference in slopes of the polynomials, we decided to do this approach, and that's when we found temperatures in the literature, and then we converted them into pressures, and then we estimated a conservative error bar after with all of those considered.
Okay. So I guess the temperatures at the surface I get, and converting to the pressure, I understand. And how did you go from the pressure at the surface from Voyager to the pressure at 1400 on Voyager, right? Because those temperatures are all going to get you to the surface pressure of 12.5 plus or minus 0.05 or 0.5 microbars. And then did you just scale based on, I saw there was a factor of 12 you had in your thesis at one point for scaling, I think, from the surface to 1400. Did you use a model, or did you use the difference that was on the B2 results that you got? Does that make sense what I'm asking?
Yes. So after the surface the surface pressure, we then use that extrapolation, the constant value that was.
Okay.
Yeah.
Okay. That was the question I was getting. Right. Okay. All right. And I think that's all the questions I have. Thank you.
Thank you very much, Cathy. Now we can move on to next examinateur, Daryl Strobel. So comments and a couple of questions.
Okay, can you hear me? I don't know if I have a video here at all. Or do you see me?
Yes.
We
Oh, you
can
do?
hear
Okay.
you and see you.
Okay, I got this small screen on the iPad, so I apologize for the mess I had, but somehow my camera got disabled on the computer. I'm going to have to work on fixing that. So personally, I think this thesis was excellent, and that the ANA paper that'll eventually appear will probably become a classic in the field, and it'll probably be the gold standard until we have a spacecraft going by Triton sometime in the distant future to perform a radio occultation. So you have a situation like at Pluto. Basically, my main question, you normalize all of your results to intercompare different stellar occultations at 1,400 kilometers, mainly because that's what's been done in the past. But is that the most accurate place in terms of radio distance or altitude to do that normalization of cross comparing? And as an information item, the radio occultation at Pluto had as its minimum pressure 1 microbar at 1,300 kilometers on Pluto. And it would probably be better, if you want to cross compare with future radio occultations, to have a somewhat higher pressure. So the question is, might there be a more accurate choice in terms of radial distance and at what pressure you should cross compare stellar occultations?
Well, this pressure is usually used because that's the one that all occultations cross. So it's a direct measurement up until this point, except for
But I'm saying, would you recommend, say, something like going to 5 microbars as for example?
Well, that would depend if the occultations could reach that, because not all probe as deep in the atmosphere. If they're further from the centrality, they won't probe as deep in the atmosphere. So maybe 5 microbar would be too low for it to detect.
How about 3? Well, anyway, it's something to think about.
Yes.
The main next question had to do with something I wrote you. I think Bruno gave it to you. Is I think you could basically do something different with the Voyager radio occultation. I mean, based on my experience from the Pluto radio occultation, the Rex result, I mean, the fundamental thing you recover is the number density profile, as you know. And the number density profile that you have basically has regions where the density is higher at a higher altitude than at a lower altitude. And so basically the number density profile is inherently unstable to Rayleigh-Taylor instability and can't basically exist in the atmosphere as you have recovered the density profile. And before you would even reach that, if you really think the atmosphere is in hydrostatic equilibrium, then you are basically going to, at a lower amplitude excursion in density, you're going to reach a convective instability. So I think the most accurate thing you got from your radio occultation was the surface number density. And I think about a year ago, you sent me from the data itself, a value of 2.65 times 10 to the 15 N2 molecules per cubic centimeter. And so what I would do is I would take the vapor pressure curve as a function of temperature, and from that compute the evolution as a function of temperature of the saturation number density. And when I do that, I basically come out with a surface pressure that's equivalent to your number density of 13.6 microbars. And I think that's a more accurate approach than the way you took a bunch of different temperature measurements with large error bars and came up with the 12.5. So your reaction.
So, okay, so you used the density, the number density that we
at
gave
the
you.
surface, the number density at the surface as your most fundamental quantity that you got from your analysis. And then I used the Frey and Schmidt vapor pressure expression, which I think is the most accurate one available in the literature, and just computed as a function of temperature the vapor pressure. And from the vapor pressure, I also found the equivalent number density at that temperature, and the 2.65 that you gave me times 10 to the 15 gave me essentially, I think, a temperature, I'm trying to remember now if I can read the fine print, of 30, let's see. It was 37 point something. But the key thing was the surface pressure is 13.6 microbars corresponding to that density. And that basically then would up the value of using your scaling at 1400 kilometers. It would up the pressure to about 1.2 microbars rather than the 1 that you got because you had 12.5 microbars. So I think you can get more and a tighter result from the Voyager result by that approach.
Joana, maybe you can show the plot with the temperatures, with the box, you know, the boxes.
This one? Yeah.
Yeah.
So I'm not sure if I completely understood, but I'll say we wanted to use independent measurements of the temperature to be able to estimate, because that would be the number that we obtained anyway, because we obtained the number that the 13.6 we obtained the same here, because that we did this what you're saying, we did that, we calculated the density and to obtain the pressure, and we obtained the 13.6, but because that's highly dependent on the baseline, on this B1, B2, B3, that's why we decided to do a different approach and use independent measurements of the temperature.
But how did you get the pressure at 13, what is it, 73? From this plot reading off which line?
So this here?
Yeah, you have one pressure at the surface minus the pressure at 1373. And so which which line on the figure here did you use to get the pressure at 1373 to give you the 9.82?
So either one could be, because they are both, so that's why we used here the difference. So the slope is close and the difference would be close. But for this one, we used the B2 because it's the preferred that Gorola had. And so we decided to make that one our preferred. But we still wanted to compare all of the baselines just to see if they were consistent with each other. And they weren't here in the pressure, that's why.
Okay, so it's the bold green is the curve that you use for 1373 pressure.
Yes, yes.
Okay.
Gorola used the B2 for his smoothed model as well, so yes.
Now the phase curves that you got from Gorola, did he basically take care of, I mean, did he work in the framework of general relativity and include, the phase delays associated with, i.e. the sun, Neptune, since the signal was received at the Earth itself, and even including Triton?
I actually don't remember. I would have to check his.
Okay, I'm just curious because for Pluto, we included the sun, the Earth, and Pluto in the framework of general relativity to incorporate. The sun made the biggest contribution to a phase delay. So in the framework of general relativity.
Okay. So I would have to check his thesis. I actually didn't think of check for that.
Yeah.
Darrell, was it significant, you think?
I haven't done the actual numbers. I mean, in the paper, Dave gave the values. For each. The sun is the most significant one. And it I guess from his point of view, he thought it had to be incorporated at least for the radio occultations. So I mean, let's put it this way, when you use your GPS on your phone, the calculation is done in the framework of general relativity because d squared over c squared is a important contribution to locating you somewhere around the globe.
Because you need an exquisite sensitivity.
Yeah, right.
I think the error is several meters.
Yeah.
Okay.
Yeah. So, I mean, just to give you some idea of, why general relativity might play an important role.
Okay. Do you have one more question, Darrell, or?
Let me just double check.
It's okay.
But those were the, as they say, I think I wrote most of these back. The one other general comment is I'm amazed by the accuracy of stellar occultations in comparison to radio occultations. If you look at what we gave for the Pluto radio occultation, we gave error bars, I think, on the number density of about 2% at the surface. And then the error bars were growing percentage-wise, and you go up. The temperature had error bars of about 6%, and the pressure also had error bars growing with altitude. Now, I mean, some of the quotes that Joana has given from the stellar occultations are at the 1% level for temperature. I mean, if you would put up one of your error bars on your temperatures,
This? Yeah.
Yeah,
Okay.
something like that for,
Mm.
I mean, you have like, take it 1400, 1.1 microbars with an error bar of plus or minus 0.03. So if I multiply that by 100, you've got, what is it? About 3 degrees. So 3% error on your temperatures there. And at this, oh no, wait, I'm pressure. But let's see, where is there a temperature? No, there's no temperature there. See, whereas for the occultation pressure, or for the radio occultation, you've got 2/10. So multiplying by that by 100, you'd have a 20%. So do you really think you can get the temperature accurate to, let's say, 3%, where the stellar occultation data is the best?
Well, the temperature or the pressure?
Well, let's take temperature. I think that, I mean, the pressure, I mean, because you used a formula to for the temperature profile as a function of altitude, and so everything was tied to that. So what would your error bars, I mean, be on temperature, where it's best? I think you were quoting something, fairly accurate, like a 2-3% for your temperatures, which, as they say, is much more accurate than you can even do with a radio occultation.
Well,
Yeah, I mean, I have some quote on page 61 of your thesis here. You have that you can retrieve temperatures at a 0.2 Kelvin accuracy level. That's on page 61, associated, I guess, with figure 4.12. And the density and pressure profiles at the 0.1% accuracy level. I mean, which is incredible. You can't do that well with radio occultation.
May I step in?
Yeah, go ahead. I mean,
yeah. This concerns the inversion of a synthetic light curve. So with infinite signal to noise ratio, okay? So this was to check if we generate a synthetic curve and re-invert it, do we find again the original temperature? But this is a perfect light curve, okay?
Okay, so what would be for a real one?
It's just a sanity check.
Okay, but
if the direct and inverse approaches are fully consistent. Yeah. And then the secondary image, this was a way also to assess the effect of the secondary image. Okay.
But if I ask then the question, with the final result, what is the accuracy, say, of the temperature at your best radial distance?
Well, we didn't check for the temperature because we wanted to compare pressures, so we didn't. Well,
let's say then pressure. What is the accuracy of the pressure? Is that something I can read off this figure that's up? That you've got the pressure determined at the surface to plus or minus 0.4 of a microbar. So if I multiply 14 by 7 and the 4/10 by 7, that's about 3 microbars out of 100, 3%.
Okay, so that's the accuracy that we have from this event because of the amount of data that we have, and this is also the accuracy for the model that we got. So if we had another model, the accuracy could be different. So it depends on what model we used and also the amount of data that we have.
But I mean, it even transfers to the pressure at 1400 kilometers where you actually have measurements. Whether it's you have 3/100ths of a microbar for the error bars. And as I say, it's still an incredible accuracy. I mean, you know, what would be a more realistic error bar? I mean, I understand what you did, and I'm not criticizing your analysis, but the error bars seem almost, you know, incredibly too accurate.
It is true that when you mention that your error bar depends on your model,
Yeah.
when it's an observation, it's a little. Just to finish, in fact, when you're saying it depends on your model, you're mentioning about the model to interpolate from the observed atmosphere to the surface, or the overall model of the occultation.
Could you repeat?
When you just say that your error bar is sensitive to your model, when you say that like that, it's a little disturbing, because no one wants to hear that your error bar from an observations depends on your model. But maybe what you mean is that it depends on you were specific for the interpolation from the 1400 kilometer altitude all the way to the surface, so it was a general comment on your error bar even at 1400 kilometer.
No, so the error bar, it comes from the pressure of the model that we are using. So we use the model, and then doing this chi-square, that's where we get the error bar. So
what do you mean when you say, if I was using another model, I will get another error bar?
I could. It could be possible.
Okay. It's too honest for us.
Yeah.
I know. I should have
Thank you
shut
very
up.
much. Thank you very much, Joana. Maybe we can
Joana, just
well,
Joana,
what you want? Bruno, you want to say something?
just Joana, show the density profiles that you obtained from the inversion.
This is the density, yes.
Yeah, okay.
I mean,
So this gives you, this is just inversion. There is no model, okay?
Okay,
Yeah,
this is the
absolutely,
able
absolutely.
inversion. Yeah.
Yeah,
yeah, this is the straight result.
yeah. So
I can't see it, but it's also small, the error.
Yeah.
Okay, I suggest we move on and
Yeah.
to
Yeah, that's fine.
Let's
As I say, I've written these comments down anyway, so.
thank you, Daryl.
You're welcome.
So we move on to give the floor to last examiner, Thierry Fouché.
Hello, thanks Joana for this very clear and comprehensive presentation. In fact, I have some questions. My first question I wanted to ask, but they are really related to the last question by Daryl. So if you can go please to the slide 29. Okay, so there you've got a number of M, which is 54, which is the number of measurement, in fact, how do you determine this number of measurement? Where does it come from?
The 54?
The 54, yes.
So this is the free parameters, and so there's 52 for the phi 0 of the light curves we used, including La Palma because of the possible problems with the problems that it had. So then another one for the pressure and another one for the center of Triton. So
Yes.
we used all of those as free parameters.
But why 52? Can you show me the math where it comes from? Where does this figure come from?
This number?
Yes.
It's from the 52 parameters of the phi 0 of the 52 light curves. So each light curve has one phi 0. And all of those were used as free parameters.
Mm-hmm. Okay.
And then
in general, when you invert the molecular density or the temperature, for example, how many independent measurement of the density do you have on the profile?
So how many for each?
For example, if you go to again to the figure, so I don't remember in which slide it is, you show it is figure 4.7 in your manuscript. So it's the molecular density as a function of the radius. I don't remember. Yes, this one. So do you have a measurement between 1500 and on the surface, more or less, a few kilometers above the surface? But on this curve, how many independent points do you have? Do you have a point to each kilometer, the measurement, the density, each kilometer is independent to the measurement of density at the kilometer, at the altitude 1 kilometer above or below? Or is it every 10 kilometers? Or is it every 100 meters? So how many independent points do you have on this curve?
On this curve?
Yes.
I mean, this is the direct result of the inversion.
Yes, but we can maybe the red curve, for example, you can mimic it with the two parameters. It's a slope and a position at the at 0. So it's two independent parameters. I could say that. So is it really two independent parameters, or do you have more independent parameters in this curve? It's nearly a slope. It's nearly just a slope. So a slope, yes, it's just two parameters, two independent parameters. The two ends of the slope or one position, and then the inclination of the. So how many? Yes, do you have a determination of on this vertical profiles of how many independent measurement of the? You don't have an infinite number of measurements. You don't measure the density at each altitude, centimeter by centimeter in the atmosphere. So how many do you measure every 1 kilometer, every 10 kilometers, every 100 kilometers? So how many points do you have?
I mean, for points,
how many independent measurement of the density? Is it just 1, 2, is it 3, is it 10, 50, 100?
Maybe Joana, you can
trying to remember.
You can explain to us what is limiting in some way. You could say that the star has an infinite resolution. So what is in practice limiting the initial signal and the inversion?
Well, here it's just a direct result from the light curve. There's nothing limiting. The only thing that is being limited is in the temperature, because it needs an initial condition here for the
okay,
for the equation.
Yeah, I understand. But okay. So I go to
Joanna, how about is it fair to say that the number of data points on these curves are equal to the number of points in the light curve?
Yes.
Because you're, inverting it.
Yes.
I'm wondering if that helps the conversation.
But do you have is the noise not limiting, this kind of thing? Because you have light curves with a very high signal to noise ratio and some curves with a lower signal to noise ratio. So I'm sure that from different curves with different signal to noise ratio, you'll not be able to retrieve the same number of independent parameters as a function of altitude. But okay. So I think also in the manuscript, I'm missing the derivation of the actual error bars, for example, either on the number density, as said Darrell, or how do they extrapolate from the number density then to the temperature? For example, none of this curve there has any error bar on this. So how do you estimate the error bars? Is it 1K, 2Ks, or and they could be different from one to the other, different from Calais and from Liverpool, because the signal to noise ratio would be different in Calais and Liverpool, for example, and maybe ingress and egress. So how do you estimate the error bars, and then what are they exactly? We don't have any precise figure on the number density, the error bars and the number density in your manuscript.
For the inversion, what we used error bars mostly were was for this phi 0, which I left out here. But yes, this is the one that we have the error bars, and then to do the template model, we just fitted it. We didn't use error bars for the template model. That makes sense.
But phi 0 is not exactly an error. It's not ready to the signal to noise ratio exactly. It's something different.
Yeah, the phi 0 has an error bar that I didn't include here. Yeah.
It's rather an accuracy than error. Yeah.
But it's incredible it's given to 5 significant figures.
Yeah.
And these questions were related to a paper that was just put on archive very recently. I don't know if you saw it. It was Adrien Bourgois from also from the observatory, and it's proposing a new inversion method for radio occultation experiments, node-based on the Abel inversion. So and it says that it gives a better error bar than the Abel inversions, better estimation of the error bars. And was wondering if you had time to have a look at this paper, and if you have any comments on it.
No, I don't know about the paper actually. Could you repeat it?
It's from Adrien Bourgois. It was an archive at the beginning of the week, I think. I don't remember. It was posted on Monday or Tuesday. And it's entitled Determination of Accuracy Profiles in Neutral Atmospheric Properties Measured by Radio Occultation Experiments.
That's the ultimate question from a committee member.
And he's actually doing the thing, in fact, with general relativity and so on. So he shows a way to determine the error bars from that. Yes, new. Okay, so far from the inversion, I was wondering whether this, I've never seen, I think in a manuscript, a comparison of your inversion profile, temperature profile, with some radiative equilibrium models. Do we have a radiative equilibrium models of the temperature for Triton, as we do have for Pluto, made by Darrell, for example? Do we have that, and how do your profile compare with that?
a radiative?
Yes.
No, I couldn't hear the
radiative transfer model. Do you have any radiative equilibrium temperature model of the for the atmosphere of Triton? Do you know that? Do we have that? How do you profile compares with predictions and so on? For example, about the thermosphere, the mesosphere, I don't know Triton, so I was wondering whether they were predicted, and for which reason do we have a mesosphere and a thermosphere, and do the increase in temperature you measure is matching by physical reasons and numerical computation from radiative equilibrium model. Do you know that?
I don't know. So I do know that there aren't global climate models for Triton. There is this volatile model that Bertrand did this year, or is releasing this year, but other climate models there aren't.
Maybe not climate model, just 1D model. You know, for radiative equilibrium, you don't need dynamics, so you don't need GCM.
You mean thermal profile? Okay.
Thermal profile in radiative equilibrium.
This one, the one on screen.
Yeah, but not the version 1.
Yeah. So how does this profile compare to models? Is that your question?
With what we know of the composition of the atmosphere of Triton. You put CO, you put CH4, you put aerosols, and so you can get a radiative equilibrium model. How does it compare with the one you retrieved?
Let me reformulate the question if I dare. I have to say there are some published models, and also we have developed one, and it has been published at least in the PhD thesis of Melanie von Bischit. But another way to put the question is that the historical profile retrieved from the Voyager era was just to say that you had a increasing temperature due to the conduction from the thermosphere all the way to the surface. But now you have this elbow at a few kilometers altitude. And another way to ask the question is whether, Joana, you have been interested to see what could be the origin of this elbow. Absorption of solar light, hazes, something?
Okay, so we haven't looked into the origin of the elbow other than the increase from surface to the elbow, that it could be explained by the methane. But it would be an interesting thing to see the origin of this elbow and the mesosphere, yes.
Can I chime in?
Yeah.
Go ahead, Darren.
Yeah, so in Strobel and Zhu in 2017, we published a model for Triton's atmosphere. And we can get the general increase in temperature off the surface. We can't put the elbow in because we don't have a cooling mechanism. My colleague, Shi Zhang at the University of California, Santa Cruz, who I was a co-author on his haze paper for Pluto. He's working on that, and I think he has a paper that he has submitted for publication looking at haze as the explanation. You can analyze the temperature profile with the elbow and make an estimate of how much heat has to be radiated away that's both being conducted down, and also to turn the temperature max there at 50 degrees downward. So you can get some estimate of how much radiative output has to be occurring to produce that elbow.
May I step in?
Please.
No, just to be clear for everybody, the upper part called here thermosphere, the slope was adjusted to Strobel and Zhu model, so it's not retrieved.
Yeah.
Okay, so
they start at 1400.
Yeah, the upper part. It's the slope at the upper part. Okay.
It was based on Voyager.
Yeah.
I mean, the temperature above 450 kilometers altitude.
So by definition, it agrees because it was forced to agree.
Yeah, I mean, the elbow is the new feature that's, you know, for real. I mean, there was a hint of it from the Elliott HST occultation, but we not as well defined as it is here from this stellar occultation.
So to be positive, we can underline the fact that this elbow, the discovery of this more complex shape from the stellar occultation compared to what we had after Voyager is something very exciting, because at the time of Voyager, we could fit the profile by putting nothing in the atmosphere, just nitrogen. So now we need more, and it's interesting.
Yeah.
Okay. Thierry, you can move on.
I had one last question, very general question. So Pluto and Triton are very similar, but they also maybe have some differences. So what did we learn from the New Horizon flyby with Pluto that would be important for you for the understanding of Triton? What do you think of that in general, Joana?
Just in general, or the atmosphere as well? Because like we already talked about, they found the mesosphere they confirmed the mesosphere in Pluto as well, and Pluto had a more extended mesosphere, so that could the mechanism that caused that in Pluto could be the same in Triton, and that would be something that would be good to investigate, to see if that's actually the case or not.
So what do we need to do to check if it's the same mechanism? How can we build on that? You have,
I would have to refresh on the New Horizons mission.
Okay, that's it. Thank you, Joana.
Thank you, Thierry. Well, it is already late, so as you've seen, I've been had the opportunity to step in and ask questions and comments. So I will have tens of questions, but I will not ask them. And in fact, I propose to give the floor directly to Bruno, and so that he can conclude and provide his comments about this PhD thesis.
Yeah. So let me give you a few comments. So first, I would like to congratulate Joana. Actually, it's a pretty atypical observation, because usually for Pluto or other stellar occultations from the ground, we had a few quartz. For instance, in the case of Pluto, the best one I got was with 6 or 7 quartz, and I was happy with that, and we did a lot of things with that. So from a qualitative point of view, this observation was quite incredible, because there were more than 90, there was eventually 99 curves, but there were more to look at. So it was really a big part of the iceberg. It's a huge Herculean task of putting everything together. So Joana said that people send their light curves, but some of them were just observed after dinner. So they had dinner, they will observe the light curves, and they went back home. And literally, and then they just vanished into nothing. So even though some of them had some nice analysis, and they were professional, most of them were amateurs, and some of them have professional approaches. So we were kind of confident they were giving us, because I've been working with them for a long time. So we trust them because we know they are experts in those, but others were not. And then came a lot of work just basic work on collecting data, reminding people that they still have to send out the data. So some of them took years just to reply. And then the second step was to understand the atmosphere. So the ray tracing, the inversion, the central flash analysis, the haze versus transparent atmosphere, blah, blah, blah. So to put everything together was really Herculean in the proper sense of the term, because there was a lot of information. It's incredible because many light curves, many of them showing central flash, and all this problematic of the structure, the thermal structure, and then the analysis of the fit, etc., etc. So I think that Joana did the best in terms of the Occam's principle. So what is the simplest way to explain everything in the light curve, which is a spherical, transparent atmosphere. And for the moment, all the results agree with that Occam principle. So with a minimum amount of information, of hypothesis, we do get a very satisfactory. So there is no departure on any light curves from that simple model, which is very different from other observation on Titan or even Pluto, when I remember that there were discrepancies. And in this case, there is no. So it's a big achievement. At the same time, it's a bit disappointing because it's boring, transparent, spherical. But I would say that it's really took a lot of work to do this. To be back on this error bars issues, blah, 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 because it was a lot of, I would say that maybe to be more clear for everybody here in the public, what we measure is properties of a model. Okay, so when we say the pressure is this value plus or minus that value, the error bar is an error bar on a model. Okay, and we hope that the model is satisfactory. And the criterion to say that is that it can explain all the light curves. There is no big discrepancies. So the error, to reply to Darrell's comment or Thierry, the error bar is an error bar on a template. Okay, and we hope the template is good. Okay, of course. But then the assumption is that the atmosphere is the same everywhere. And this is what was observed for Pluto. Apart from the the deepest kilometers, when you go upwards, Pluto's atmosphere is extremely isotropic. So we have good agreement to say that what we got is really a good global model, and we don't see any departure from evening to morning limb and winter to summer, etc., etc. Okay. Now, to go back to this Pluto versus Triton comparison, I would say what's interesting that Joana showed that there is a mesosphere, which is not quite explained for Pluto. So Darrell worked on that and other people, but there is no clear explanation why there is a mesosphere on Pluto. I think it's still debated. I guess Darrell, you agree with that, so not fully explained. Anyway, I think it's interesting to show that in this case of Triton, there is an evidence for a mesosphere, which is not, as far as I know. You mentioned some incoming work, but it's not explained. So to answer Thierry's comment, no, for the moment we can explain the inversion layer through CH4 heating. The thermosphere is just adjusted to models, so we have no information of that. But the mesosphere is a brand new result, which is not explained for Triton and which is still debated for Pluto. So it's an interesting result that both atmospheres have a mesosphere, which is not fully explained or clearly understood, as far as I know.
Well,
Okay.
I would make one statement that Triton lives in the magnetosphere of Neptune, and we had to invoke magnetospheric particles as a source of energy to get the high temperatures from the Voyager solar occultation.
Now, okay, and just to finish about the probing the deepest part of the atmosphere, Joana, can you show the the synthetic model showing the primary and secondary image. Yeah, this one. Yeah. Okay. So basically, to answer maybe Candy's comment, you see that the secondary image is on the negative side of this plot. Okay. So when you compare the primary image, which is in, if you swap that green profile in a mirror symmetry, you see that the secondary image is much smaller than the primary image. And due to noise, the secondary image does go to the surface, but it's small compared to the primary image flux, and it's buried in the noise, okay? So this is why we are blind in some way. As we go below 8 kilometers, we do have a secondary image, which is deeper than the primary image, which eventually reach the ground at minus, 1,000. So we are blind to that. And the hope is maybe if there are hazes or clouds, there could be a small discontinuity when the secondary image disappears, but we didn't see that. So, but maybe for future work, we can include hazes or clouds and in a second order approach, see if some of the best light curve shows those small discontinuities, revealing the disappearance of that secondary image in the haze. So I think it will be worth having some models from you. And then with those models, look at the drop of signal caused by that cloud or haze, and then compare that to the data. And I think that for the moment, Joana didn't show any evidence that there is some hint. When you look carefully on some light curve, you see small wiggles. So maybe there could be some hint that something is going on, but it's not like for Titan occultation, where without haze, you cannot explain the light curve. It's obvious just by naked eye, okay? You say, okay, this is a synthetic light curve, this is observed light curve, and the star just disappears. So you have to put some absorbent. But my point is, Joana didn't show that there is any discrepancies from the transparent model. And maybe this could be the case in an extension of this work for finer effects or second order effects, quotation mark, okay.
Bruno, this is a defense, so you don't have to answer to
No, my point is to make clear a few things, okay?
Okay.
And
do you have other comments on the?
Yeah, and then the last thing is a comparison from our results and the other teams, which is the pressure versus time. Yeah, again, my experience on other observation, not Triton, but Pluto's occultations, is that we really have to compare the ray tracing models, because I have clear examples where for the same event, people are using different approaches or different ray tracing. And I will not give you neither the names nor the experiments, but for the same...
I would like to jump in here for just a second.
For the same event, we got different values just because people use inconsistent models. So we are measuring a model, and we have to be sure that using the same data, we use the same protocol, and then get at least, it may be not better than others, but at least it's consistent with our own method. So my point is that even if everything is shifted up and down due to some systematics, due to the template model, at least the trends like increase or decrease will be detected. But then if we compare pears and apples, we can say anything. And my experience is that many wrong things were stated before in other occultation, just because people were comparing the data from team A and another data point from team B. And it was not correct because they were using different approaches.
So Bruno, I totally agree with what you just said, but I do want to point out that nitrogen is very volatile, and it's actually not surprising at all to me to see temporal changes.
Yeah, sure. I agree with you, but once a consistent approach has been applied. Okay.
Yeah.
This is the very first step. And
Right.
We look forward to that. So Bruno, one last word.
Okay, so
Yes.
no, just I mean, I would stick with that. I mean, global view that Joana could have, which was really from just data analysis, modelization, everything, inverse and direct approach was really a nice global package that I think which is the best that could have been done at first order, at least on this event. So I can congratulate her for that. Thank you.
Can you comment on the difficulty of the work during this crisis, the coronavirus crisis? Oh, that.
Oh, me?
No. Yeah, I'm asking you the question.
Excuse me? Is it a question for me or for Joana?
No, it was a question for you, maybe.
For me. Okay.
If you wanted to say anything, but you don't have to. We can move on.
Yeah, it was difficult because sometimes when you are side by side, it's much easier to see little details than on a Zoom session, which was really, I mean, yeah, it was also a problem because especially to talk about all those details, sometimes it's much better to be side by side, and it certainly, I mean, made things more difficult at some point. Not the global approach, which is okay, but all those dirty details that are much easily passed between people if you are face to face in the same room.
Thank you. In fact, Joana, if you want to make a comment on this specific point, you can now, but you don't have to.
Yeah, it was that, and just all of the insanity that was being closed in the house for a year. Yeah.
Okay. We got it. The message was clear. Well, thank you very much. I think we can finish now this phase of the defense. So we are now going to the committee. We are now going to discuss, and then we come back online. So I let the technical organization do the